Well, back with some more fun with 9Front on ARM chips. Still working on the all-winner A64. Today I'll show how to read the temperature sensor and how to make that into a file. And I'll touch on the Ethernet driver, even though it isn't finished, and have a bit of a rant about memory management. So the datasheet has registers for the temperature sensor. It has some neat features too. Like it can throw an interrupt in case of an alarm or a shut case. So alarm can be used to tell the software to throttle down the CPU, and if that doesn't work and the temperature goes up more, it can send another kind of interrupt to tell the CPU to shut down. Let's see here. So there are 3 sensors on here. Yep. So there's one for the CPU and then 2 for the GPU. And there's also some fiddly bits down here where you can do some calculations to put in your various timings and stuff. And before we get into poking the temperature sensor, the first thing is to make sure that everything is turned on. So again, these ARM chips are often meant to go into portable equipment, so things are often turned off by default to save power. I already wrote some code that would read the clock gates and return a formatted list of what is turned on, and the THS sensor, which is the thermal sensor, and it was reported to be off. But the gate itself is only part of it. Most of the other things included on these chips have other ways to adjust the clocks on them. So right now, if I try to write into the thermal register, it just won't do anything. And the datasheet lists 3 things for the THS thermal sensor. A register here for various clock settings. And then there's a bit for the gates themselves. So that would be here. So this is just 1 bit in a register for all various other things. And then there's another option for resets. So let's see, where was it? Yep, there it is in the reset block. And then when it comes to just notes on doing this, it does mention that one should send the reset signal before doing the clock gating. So for now, I'm just going to write this quick little function here. This will just flip that bit on the clock register to turn it on. And then I'll go in and flip the bit for it on the reset, and then flip the bit for it on the gating. So now that the clock is enabled and the gate is open, the thermal sensor will now accept bits to be written to it and actually spit out temperature data. So back to the thermal sensor. So I plugged in a bunch of stuff here. Now these are all the offsets for the various registers. I put in some stuff here to make it a little easier to flip some bits. I didn't put in everything, but I just did enough here for some basic use. Down here I have some things for some stuff I might want to adjust. Something to keep in mind about this kernel stuff here is that you can't be using floating point numbers. For one, the code to deal with them is often a separate library that isn't included, and it may also be the case that the floating point unit needs some extra setup which might not be done. So in this case, there was a formula that looks like that, but since it had decimals in it, I just bumped everything up by a few decimal places. So yeah, the real challenge with like kernel hacking really is that you can't just pull in some library, and you have to get creative using basic programming skills, doing stuff with bitwise operations and unsigned integers. All right, so now down to initializing this thing. So I got this little thing here, goes in to make sure the clocks are turned on. Then set some bits in these registers for enable the calibration, and then it wanted a couple time values in here. There was a filter option, which would sort of average out 4 things. So let's see here. That was filter, yeah. So the default, it says it wants to default to 4, so I just went ahead and stuck with that. But again, you know, if I'd just written filter enable in there, that would set that bit to 0, and so I have to write it back in. So it's something to keep in mind anytime you're doing this sort of thing. Next, I set up the interrupts. But first, just a good practice to make sure whatever interrupts are in there are cleared. So in this case, it was status. So it informs me here that, you know, writing a 1 will clear the interrupts. So once I clear the interrupts, I go ahead and set it. So I went ahead and set alarm and shut down interrupts for sensor 1. And then there was another sort of time value that's put in that register too. And let's see. Once all that's set, I then read back control 2, tell it to modify it to turn on sensors 1, 2, or 0, 1, and 2, and then write that back to actually get everything turned on. And then this last little bit here, this interrupt enable, that's part of the portable code for the operating system. And this is so that it'll actually watch out for interrupts coming in on, this would be the interrupt number. This is the function to call if interrupt happens on that number, and then a few other options that you can put in. The interrupt function itself is pretty simple. So when it gets called, it'll just read the interrupt status, write that exactly back, which should clear all the interrupts, and then check to see which particular interrupt was set off. And so if the alarm gets set off, it'll just print the CPU is hot. If shutdown is thrown, then it'll let me know the CPU is on fire. The actual sort of data readout is pretty straightforward here. So for each of the sensors, I read that particular register. So we got 0, 1, and 2. Oops, that one's actually supposed to be a 2. So right now I'm accidentally reading those ones together. Huh. Anyway, so I pull that out, I mask it out, so that's just that because, let's see, where's that PDF? There we go. So the sensor data is not a full 32 bits, it's just these first 12. And since I don't know what could possibly be in there, you know, it should be zeros, but it could be anything else, it's best just to mask it out to make sure. So read that and then send it up to this little formula. And that does that little number crunching job and returns just an integer value in Celsius. But this is a Plan 9 system, and so the expectation is that we can access this stuff by reading a file. And luckily others have already put in the effort to make this fairly easy. There's already a template for an Arch device. This is a file system interface for architecture-specific things. The CPU temperature is often placed in here. Since it isn't something generic like a USB device or a PCI card. I didn't write most of this particular one. Credit goes to Sir Geoffrey, who is also working on this to port 9Front to the PinePhone, which also runs an A64 chip. So all the way down here, I added a little bit. So this is saying to add my file, it'll be called CPU temp. That's the permissions. This is the function to call when it's read, and if I had a read option, it would be there. So earlier I already did one to adjust the CPU clock speed. So there's one function to read it, and then there's another one if I was going to write a value into it. And then here is the function for actually reading the thermal sensor. So it grabs the 3 different ones, shoves them into these variables, and then just basically does a real quick and dirty format here. Just puts them all in a row with on each one on a new line. Then this read string function here, this comes with the operating system. This actually handles sending that off, and it will return how many characters were read out. And with all that done, this is what it looks like. So there's a now a CPU temp file in the dev directory. That means the dev arch device is bound to /dev, and when I read it, it spits back out the temperature. So on to the Ethernet, and I wish I had more to show for this, but right now it's currently broken. For now though, I can give a basic breakdown of how these sort of things are supposed to work. So a lot of this will also apply to Wi-Fi. So networking consists of two main parts, the MAC and the PHY. The MAC is the part that gathers up the data off the network and feeds it to the operating system, and it has the ability to read and write directly to RAM. It does this by checking descriptors, and these descriptors are assembled into a ring buffer, and the all-winner manual here actually has the list for the descriptors. So it consists of 4 32-bit unsigned integers. The first is a status descriptor, and this will cover what's going on with this particular bit here. The next is the size, and that'll have whatever the size of the data is going to be, an address of where that's going to be stored, so it's going to be a physical address there, and then the address of the next descriptor, which will just point to the next one. Descriptors can vary between manufacturers. The MT7688, for instance, didn't need this next option here. Instead, you'd tell the MAC the exact number of descriptors in your ring, so it knew when to jump back to the first. However, that meant that the ring had to be contiguous and properly aligned in memory. So depending on how your MAC handles descriptors, you initially set up the receive ring with some flag that tells the MAC if it's available for use, and then allocate a bunch of memory blocks for it to stash incoming packets. When the MAC gets the incoming packets, it will change the status of the descriptor, add in the size of the data, and write the data to the provided memory space. In this way, if you haven't read the data and cleared the status, the MAC knows when it loops around the ring to stop processing any incoming packets until you've had a chance to clear them out. The transmit ring doesn't need as much setup because you put in the status and assign the buffer as you have packets to transmit. So the MAC is connected to what's usually called a PHY, that'll be PHY, and that's for the physical part of the networking. So you plug the cable into that, and this can be copper cable, fiber optic, or radio. There are a few industry standards for this, so documentation may use terms like MDIO, MII, RMII, or GMII. So in this case, the MAC has registers to talk to the PHY, and that's with this me command and then me data registers. So when I was doing the MT7688, since it had an Ethernet switch built in, this part of those registers were on the switch instead of the MAC. But reading the me interface here can provide some ID numbers for the PHY, can also read and set the speed of the link. Some of them can get pretty sophisticated, as the purpose of the PHY is to turn your ones and zeros into some other sort of signal to be transmitted on whatever it's physically hooked to. So on to how 9Front handles all this. So pardon the mess here, but this is all going to be a work in progress. In the kernel configuration file, I put an entry for the name of the Ethernet driver. So it's file name there. Add a little bit for etherme to say I'm using that also, and to pull that in. The portable code for building drivers will look for that name with link on the end. And this will be called whenever the driver's like started up. It'll do this add Ethernet card thing, and it will look for that function to call to actually set everything up. And then when it runs that one, this PNP function, this basically just initially just goes through and kind of sets up these this ether data structure with the pertinent information. So it's got IRQ number, a controller data structure, you know, your speeds, your maximum transmission unit. Important one here is going to be this one. So it's going to look for an attach function for when it's initially attaching the network interface to the machine and setting up the file system for that. So during the boot process, when it's ready to set up the network, it's going to run this attach function. So it's going to come down here. First thing is I have a little thing here that's basically set some things in the system control registers for initializing that. Then I come down here and I allocate some memory for the descriptors. All right, then I initialize the receiver rings. So it just runs through each one at a time, allocates a block of memory, puts that block in the descriptor, gives it the physical address of the next descriptor, sets it up basically saying that this is an unused block here, and then this is to tell it like how big of a how much data it can take. I do a simple one for the transmit ring, so all it really needs to know is what's the next ring. Then I do a soft reset, so that should just like basically clear any settings that are currently in the Mac. Next is, this is a setting I found. It was basically just the default, but just made sure that it's written back in. And then I actually give the physical address of the descriptor rings to the Mac. I then tell it what I want to throw an interrupt for. So this is going to be for if there's a receive happens, a transmit happens, or if either of their buffers get out of whack, it'll sort of kick the thing. A couple different options I was playing with for telling it to start that interface of reading and writing to the memory. And then, yeah, these are basically all just sort of enabling things. Some stuff for the handling the me interface. And then the last one is to fire up some processes to handle the actual transmit and receiving of stuff here. So on the receive end of things, all right, so first thing it does is it, so it's going to get a descriptor here and grab the address of the current descriptor in use. And it's just basically going to check to see if it's been used or not. If not, it'll sit here and wait. When it is used, it'll grab the, let's see, the length here. That would be, here it is. Oops. So it'll grab the length of the incoming bit of packet from the descriptor. It'll set a block for the data. It'll then send the length of data going into the block. And then it'll move that block to the input queue. And this Ether IRQ thing here, this comes with the operating system, and it'll make sure once it's read the block, it'll make sure to free it. But I do have the little if here. If there's some sort of fluke with the length and there's nothing there, I'll manually free it down here. And then once all that's done, I basically allocate a new block, put that back in this descriptor, set the this little thing here, which tells the Mac that it's free to use, how much data it can take. And then, so quite a few of these little DMA flush things here. I'll get back to that later. And then it runs this little formula, which will either bump up to the next descriptor in the ring or loop back around to 0. So on the transmit end of things, I'm going to come down here. I'm going to read something from the output queue, put it into a block. So if the current descriptor isn't free, which is what this thing checks for, then it'll sit here and wait. And once there's a free block or a free descriptor, it'll move down. It'll give me the length of data that the operating system gave me. I'll set the address to the address of that block. So that's the physical address of it. Tell it how big it is. Set the status to let it know that the Mac is ready to go ahead and do something with that block, flush it out. And then this is down here to make sure that if the actual start bit hasn't been flipped, it'll flip that and get the whole thing going, and then the little formula to move on to the next descriptor or loop back around to 0. So on to the interrupt end of things. Oops. Let's see. Ether interrupt. So when an interrupt gets called, this function will get called. It'll be passed the Ether data structure too, so I can fill out everything from there. I'll read the current interrupt status from the Mac, write back ones to clear it, and then basically just check to see which interrupt got thrown or collect some data. For some reason I got a spurious interrupt. And these will basically just wake up those receive and transmit functions. So when it comes to reading and writing commands to, oops, here it is, to the Mac, that's pretty simple. I have a rather simple little functions here. Also one for the system control register, since I do have to check that. And yeah, they just basically just write things directly to these pointers or grab it from there for these sort of memory mapped devices. The Me interface, on the other hand, takes a bit more. So on the read end, we write to the Mac that we want to read from a certain address and register in the PHY. This thing also takes this little clock thing. Since it runs at a different speed from the system, there has to be an adjustment for that. It then checks it over and over to see if it's busy, and when it's done, it can read the data out of the data register, and then sends that, returns that value. On the right end, so this time we do it kind of backwards. We put what we want written into the data register. We then set the address in the register. There's also a little flag you have to flip here to say, by the way, I'm doing a write. Then we send out the command and we keep checking until it's no longer busy, which means it's actually ingested the write. So this driver isn't completely working yet for a few reasons. First, when searching for other troubles, I found that the Pine 64 had troubles during the chip shortage, sourcing these PHY chips. Also came across some discussions about the A64 being used on a Orange Pi board, having issues where the Mac hangs when doing the soft reset, which I've also been having issues with. And the other is an issue more to do with how computers work in general and how ARM processors in particular handle this. So that issue is caching and memory management. If you're old enough or you're into retro computers or consoles, early computers generally did one thing at a time, and so you could just let the one program access the RAM as it pleased. Later, as multitasking became more of a thing, it became sensible to keep one program from accessing the RAM used by another program, or the RAM used by the kernel. So now, all the programs you run are given a virtual set of addresses, which then get translated into physical addresses behind the scenes. And this sort of ability was added to the hardware. So every CPU type has a way of setting up virtual memory. This is usually called a memory management unit. So the other thing that was added to CPUs to increase performance was cache. This is a small amount of memory on the CPU. This allows the CPU to fetch some bit of data, do several operations to it, all without needing to send it back and read it back from memory on every operation. Where this becomes an issue with writing drivers is that for my writes to set the registers and to take effect on the hardware, they need to go all the way out to the memory mapped address of the device. The other issue is that if the device itself also needs to access buffers in the RAM, or those descriptors used by the Ethernet device, they also need to go all the way out to RAM. So the issue is that what can happen with is that the Ethernet driver can say write something to the descriptor, but that change might not make it back to RAM by the time the Mac device itself goes and reads that descriptor from the RAM. So when it comes to writing to memory mapped, like the Mac device and stuff, ARM did provide a solution. So when I do the initial setup of the memory management unit, there's a bit for setting up the virtual addresses for memory mapped I/O. So for the A64 chip, let's see, there it is. That's basically where the memory mapped I/O devices start. That's their physical address. That's about how far it runs. So on the initial setup of the virtual memory, there's a separate part for setting up the virtual I/O. And when you see the attributes it's given, one of the different ones is it gets this little device attribute. However, let's see, that'd be RAM, should be it. Yep. So all the rest of the kernel memory though does not get that. So it's just set up as you know, regular memory, and it is cached. On the MediaTek MT7688 chip, that was a MIPS-based chip, and the MIPS solution to all this is to have a region of virtual addresses which mirror the kernel memory, but access it without caching. However, ARM does not allow one to double map a physical address like this. One of the ways the Linux people dealt with this was abusing a function that would remap an address range to act as a device. However, this supposedly would cause unpredictable behavior in some versions of ARM CPUs. So the proper solution would be to set aside a range of physical memory, tell the system to not map it, and thus the kernel should not use it, and then separately map it as uncached RAM, and make a memory allocating function that would use the uncached memory specifically. But this does take some advanced planning. And I know that later on I will also be having an issue with this, because if I want graphics and a frame buffer to go with it, it should also need a chunk of the RAM set aside with some special mappings. The other option, which goes all the way back to that DMA flush thing I mentioned, is that you can issue specific instructions to do things to the cache. So that DMA flush function, which I borrowed from some other 9Front ARM64 kernels, does a couple of these little functions here. So thankfully, like, someone left notes on exactly what these are. ARM is actually really good about documentation. Let's see. Bring up the browser here. So if I type in ARM v8 and then one of those things, I can bring up a nice little page explaining exactly what that is and how to work with it. So like this one here, it invalidates data cache by address to point of coherency. So that means this one here you give it an address and it will sort of flag it as being invalid, which would sort of make the CPU go fetch some more from the system memory. But this is not the best option in terms of performance. You know, if it was set up like just writing to uncached memory, then it would just handle all this in the background. In this case, you can see that, you know, these are branches here. I'm going to have to jump to some function, jump to another function, run some stuff, and then jump back to my code. So it's kind of an ugly hack at this point until I can get settled down to figure out exactly how much space I'm going to have to carve out and set that up. So I'll go ahead here and see how far I can get with the network on here. All right. Ether 0. Well, it seems to be on. Let's see if I can get it to, pull down a address from the DHCP server. So sometimes this works, sometimes it doesn't. Still waiting. Ooh, didn't say no. Let's see here. Oops, cat, that'd be net IP self tab. Oh, so it did indeed get an IP address this time. And there are packets going in and out, but for some reason, most of them say they're bad. Let's see, IP ping. Sometimes a flood ping will work better. Oop. So partly working, but definitely not very quick. There's some definite lags in here. So a lot of tweaking to get the performance working. You know, 10 out of 32 packet loss. And this is also a gigabit interface. I think right now it's only running at 100 megabits. I deliberately put a 4-cord cable on here to force it down that way. Gigabit Ethernet's actually pretty quick, so there's some extra timings and stuff that have to be set. It can be quite a bit more fiddly. But yeah, 30% packet loss isn't really very useful. Oh, this one looks like it ran a little bit better. Nope, the same. So yeah, there's a little bit more to play with that. There's definitely a lot of moving parts on Ethernet driver. One of the downsides is though, and I've mentioned this about some of these ARM chips, is that when these people make these little single board computers, they're using chips that are designed for some other purpose. So if like this A64 chip was meant to go in like tablets or phones, then they made this, it just might not have a very good Ethernet setup in it anyway. It might just be the bare minimum. This also comes up with a Raspberry Pi, since it was meant to go in TV boxes. Most of the configuration for it is actually handled by the GPU, which makes sense on a TV box. You know, that's largely how you're interacting with it. But it doesn't make a lot of sense when people use it for a Raspberry Pi that sits there as a server with no graphics hooked to it. But yeah, enough about ranting about that. So, well, remember to have fun.